Hi everybody. Normally when designing a controlled system, the focus is mainly on performance. For instance, what is the required response time? What is the required settling time? Is overshoot allowed? Which disturbances have to be suppressed and to what level? What is the required tracking accuracy? What is the requirement on the static error? And so on. But of course, stability is just as important as performance, because when a system is not stable, there is no working control system, and mechanisms can get broken or unsafe situations may occur. This video is the first one in a series of two, which discusses stability in the frequency domain. In video number two, we will focus on stability criteria and we will discuss stability margins. In this video, we will discuss the basic aspects of stability analysis in the frequency domain, focusing on the oscillation condition. And to do that, I have drawn a feedback system over here. And in that feedback system, we see two blocks. We have block number H1 and we have a system block number H2, which are transfer functions. And H1 is in the forward path and H2 is in the feedback path. So we have a standard feedback system and the output over the input is H1 divided by 1 plus H1 times H2. Remember, that is the standard situation. Now I'm going to do with you a thought experiment. And in that thought experiment, I'm gonna wash out this feedback loop over here. And I'm going to insert a vibration signal. And that vibration signal is put as an input over here. And I call that X. And I measure the output over here, Y. And what I'm going to do is define the criteria in which that signal X keeps on oscillating in that feedback loop. So keeps on oscillating through the systems H1 and H2. Well, now let's define what the output signal Y is when the input X is oscillating in that system. So when we see signal X, we see that it's amplified with -1 due to the minus of the subtraction component. Then it's fed through H1. Then the signal is fed through H number 2, and then it's the output signal Y. So Y equals X times -1 times H1 times H2. Remember, when we have that signal X over here, it starts moving through that subtraction point over here through H1, through H2, and then it's back, it's Y. So now let's look under which conditions Y is equal to X, or in words, under which condition is that input signal X oscillating in that feedback loop. Well, that is the case when this part of the equation, -1 times H1 times H2 is equal to 1, because in that case Y is X times 1, so Y is X. So when this is 1, then my system is oscillating. So that is the case when -1 times H1 times H2 is equal to 1. Or we can say when H1 times H2 is equal to -1. So when that is the case, then a frequency which meets this condition, which is the oscillation condition, that frequency, the signal with that frequency, keeps on oscillating in that feedback loop. So this is what we call the oscillation condition or the oscillation criterion. Oscillation condition, right. There it is. So again, when signals with a frequency which meet the requirement that at that frequency H1, which is a transfer function in the frequency domain, times H2, which is also a transfer function in the frequency domain, is equal to -1, then the signal with that frequency keeps on oscillating in that feedback loop. Well, we can rewrite that oscillation condition also in another way, because H1 and H2 are in the frequency domain, so they are complex numbers. And in the complex plane, remember, we have a y-axis and we have an x-axis, and that x-axis is the real axis, and the y-axis is the imaginary axis. And that point, number 1, is a point which is on the negative real axis. It's over here, -1. So now we can define a vector towards that point -1 over here. And when we look to that vector, it has a length, an amplitude of an absolute value, which is equal to h1 times h2, which is equal to 1. And when we look to the phase of that vector, so the phase angle over here, we see that it's minus 180 degrees. Or we can say the phase, which is the argument of h1 times h2, equals minus 180 degrees. So again, when we have signals which meet these conditions, so that the phase of the systems at that frequency are equal to minus 180 degrees, and the amplitude of all the systems in that feedback loop at that frequency are equal to 1, then the system is oscillating at that frequency. All right, so what we can also imagine that when there are more feedback systems, or more systems in that feedback loop, I should say, suppose that it's not only H1, but it's also an H3 in that feedback loop, of course, then also that H3 has to be taken into account. So the oscillation condition over here says that all the systems in the loop, when they are equal at a certain frequency to -1, or when all the systems in the loop, when the absolute value of it is equal to 1 and the phase of all these systems in the loop is equal to minus 180 degrees, then the system is oscillating at that frequency. You can also imagine that when the phase is minus 180 degrees, but when the amplitude is higher than 1, then happens the following, that signal X is coming into that system. It goes through the subtraction block through H1 through H2, and H1 times H2 is in this case higher than 1, so it gets amplified, but the phase is still the same. So it gets amplified, etc. So it blows up, and then your system is unstable. So you're unstable when the phase is equal to minus 180 degrees, and the amplitude of all the system blocks in the feedback loop at a certain frequency is higher than 1. Well, that is the oscillation condition, and we have seen when a system becomes unstable. In the next video, we will discuss how systems can be analyzed with respect to the stability criterion. Thank you for watching, and I see you in the next video.